Okay. All right. So last time, where I got to was a formula for the time variation of energy. Oops. Okay. And so we defined the energy to be the kinetic energy. Plus, if there was a potential force being applied with potential energy V, then that's the potential energy. Okay, and so we calculated that d by dt of E of gamma prime of T, so the energy along a motion of the system, so we're following a motion gamma that satisfies the forced geodesic equations. And we calculated last time that this was okay, given by a formula like that. Okay. All right. And so here, F were other non-potential forces that are applied to the system, okay? Because if it has a potential force, then you just soak the potential energy up into the energy, and then that formula still remains true. Okay. And so let's look at some special cases, okay? All right, so first, if there's no non-potential external forces, so F is equal to 0, then energy is conserved. Okay, so its derivative with respect to time along motions of the system is 0, so it's constant. All right. So if F is a dissipative force, all right, so we called this a Rayleigh dissipative force last time. Okay. And so remember what that meant. That meant that R is a symmetric a symmetric a bilinear mapping, and it's positive semi-definite. That's what it means to be a Rayleigh dissipative force. Okay, then d by dt of the energy. Okay, all right, so now I'm going to stick F to be minus R flat. Okay, so this is going to be minus R flat of gamma prime of T, like so. But by the very definition of the flat map, that means that this thing is equal to a minus R of gamma prime of T, gamma prime of T. Okay, that's just the definition of the flat map. Okay, and I know that this is because R is positive semi-definite, this is less than or equal to 0. Okay, and so if I have a dissipative force like the kind I'm talking about, then energy is non-increasing. Okay, so a dissipative force is called a dissipative force because it dissipates energy, or at least it doesn't leave energy constant. If it does anything to it, it'll decrease it. Okay. So there's a kind of force that we talked about last time, and so you might wonder: are there forces that you can put in here which don't change energy? Okay, so in other words, are there forces for which this thing is always zero? And you can kind of take some guidance from the dissipative case. So in the dissipative case, when R is symmetric, okay, or symmetric and positive semi-definite, but mainly symmetric, ensures that this quantity will always be positive, and so the rate of change of energy will always be and so with the minus sign, the rate of change of energy will be non-positive. Okay, but what if R here was skew symmetric? Okay, I mean, it's not for a dissipative force, but maybe some other kind of force, it's skew symmetric. So if R were skew symmetric, then because I'm giving it the same two arguments, it'll always be zero. So those kinds of forces have a name. They're called gyroscopic forces. Okay, so it's rather like the Rayleigh dissipative case, except rather than being positive and semi-definite, it's skew symmetric. Okay, so I'm guessing you're familiar with that term, but in case you're not, it means that C, when I give it two vector arguments, let's say U, Q, V, Q, okay, it's minus C of V, Q, U, Q. Okay, so when you swap the arguments, it changes sign. Okay. All right, so gyroscopic forces, notice, do not change energy. Okay, and exactly for the reason that I sort of outlined before I started writing this, and that is that if instead you put C here and C is skew symmetric, then because you're giving a skew symmetric bilinear mapping, the same argument, it'll be zero. Okay, so the equations of motion are not the same. There's still a force being applied to the system. It's just that the force doesn't change the energy. It'll change the motions, but it won't change the energy. Okay. All right. Okay, so so that's all I am going to talk about forces. Okay. All right, so for the last 3.5 lectures of the course, we're going to talk about what are called nonholonomic constraints. Okay. Now, we started at the beginning of the course with 3 examples, right? So we had our planar body example. Okay, then we had our stupid robot example. All right, and at the beginning of the course, we also talked about this rolling disk example. Okay, and we carried on talking about these, and last time we, for this one, we completely wrote down the equations of motion, and then I just didn't want to calculate Christoffel symbols and everything for this one, but in principle, we have the equations of motion for that, but we stopped talking about this at some point, okay? And the reason is that that system's different than the other two, okay? And the reason that it's different is, okay, this has a no slip constraint. Okay, and so we'll talk about exactly what that means, but let me tell you kind of in words what it means, is that, so we decided for this example, and so for this one, we decided that Q was S1 cross R2, okay, and for this one, Q was S1 cross S1, and for this one, we had Q is S1 cross S1 cross R2, okay, and the idea was we had a spin angle. I forget the order I gave these, but we had a spin angle, a roll angle, and then the position of the point of contact in the XY plane. Okay. But there's more constraints happening in that system than just that we take motions restricted to lie in that submanifold of Q free. We have a constraint that says at the point of contact between the disk and the plane, right? That point of contact of the disk with the plane, that point in the body at every instant of time, its velocity, its spatial velocity has to be 0, right? Because it's in contact with the stationary plane, all right? And so that's a constraint not on the position of the system, which is kind of what we did in all of these cases. So we had Q as a submanifold of Q free, and so that gave us position constraints, right? We constrained the configurations always to lie in Q. With this kind of a constraint, we're not actually constraining the position of the system, we're constraining the velocity of the system. Okay. Okay, so the constraint is on the velocity and not the position, not the configuration. Okay. So I'm going to, so what we're basically going to look at is we're going to look at velocity constraints, okay? And those are what are called non-holonomic constraints. That's the term that you see used in the literature. Sort of a more descriptive term, in my opinion, is velocity constraints as opposed to position constraints, okay? All right. So let's look at a couple examples. Okay, so we're going to look at 2 examples, and I'm going to treat them kind of both in the same way. One example is going to be very simple, and these 2 examples are very similar, but they're different in an important way, which we will understand. Okay. So the first example is just a disk moving in a line. Okay, so it just moves along a straight line like so, but it rolls. Okay, so this is a disk rolling in a line, and the other example up here is a disk rolling on the plane. Okay. All right, so let me do a little bit of modeling here. So I'm going to write S1, S2, and S3 will be, well, let's see, S3 will be coming out of the board by the right-hand rule. And then my disk, like so. So here's B1, B2, and B3 again will come out of the board. And there's going to be this angle theta. Okay, and then there's also going to be this translational distance x. Okay. Now, instinctively, what do you think the dimension of the configuration space for this system is? There's kind of two reasonable answers. What do you think? Someone want to give one of the two reasonable answers? Yeah, so two-dimensional is one of the two reasonable answers. The other reasonable answer is one-dimensional, okay? And you say two-dimensional because I just drew two coordinates for the system, right? X and theta. But somehow intuitively, or you feel like this is really just a one degree of freedom system, right? So it rolls, and there's only one motion. And so in other words, what's really going on is there's two variables, X and theta, but they're really coupled, right? And they're coupled by a velocity constraint, right? So what we're going to do though, when we model this system, is we're going to work with Q being two-dimensional, and then we're going to put a velocity constraint on the system, okay? All right, so we're going to take Q to be, okay, so we're going to go back to, beginning of the course type stuff. To write R's and big R's and little r's. Okay, so that's going to be our big R. And then there's going to be a little r, which is just going to be X. And then the disk is going to have some radius, which I'm going to call rho. Okay, so in the S2 direction, I have rho and then 0. Okay, so that's my Q. And so this is my little r. All right. Okay, good. So I'm not really interested in anything. So, I can go through and do all the stuff with kinetic energy and all that stuff. Okay, I'm not so much interested in that right here. What I'm interested in is that linear velocity constraint. Okay. Okay. So how do we model the fact that as the body moves and it's in some configuration, big R and little r, there's going to be that point of contact, which is going to be whose spatial velocity will be 0, okay, because it's in contact with the ground and the ground is stationary. Okay, so let me write this point here as X R R. Okay, so that's going to be so X R R is the spatial coordinate, or the spatial vector, or in R3, giving the contact point. All right, so what I want to do, I don't want that spatial point though, because I know that that's stationary. What I want is I want to express the body point. Okay, so in the body frame, I'm going to have some point which is going to express the position in the body of this point. Okay, and so chi, and so I'm going to use the notation that I used when I talked about kinetic energy, right? And I wrote down spatial and body coordinates for points. And so we used chi. This is the body vector of the same point. Okay, and when we did kinetic energy, we had this formula that related the body coordinate of chi of a point and the spatial coordinate, and that formula was this. Okay, and that in particular holds when I take the point of contact. Okay, all right. Okay, so now I actually know some things about these various objects, okay, because I have an actual physical system here, and I haven't actually included anything about my specific system in any of this stuff yet, okay. And so I know that x r is x 0 0, okay, right, where x is just the coordinate that describes the point in Q. Okay, and I therefore I have that x r minus r. Okay, so I'm interested now in this thing. Okay, is equal to therefore 0 minus rho 0. Okay, just exactly because r is equal to that. All right, and so therefore chi r is equal to, all right, so now I'm just going to use this formula with chi rr and xrr in it, and so I'm going to get that chi rr is, so let me get it in the right direction, so it's going to be r transpose x r minus r. Okay, okay, and so this is minus rho r transpose s2, okay, because this point is minus rho x s2. Okay, okay, good. All right, so now now I know that point of contact has to be stationary. Okay, okay, so the point of contact is stationary. Okay, and therefore I know that x r dot is equal to 0, but that's also r dot plus r dot chi r. Okay. Okay, and so therefore what I get is I'm going to now substitute chi rr into this formula, and I'm going to get the 0 is equal to r dot minus rho. Okay, so then chi is equal to r transpose s2 times rho. So this is going to be r dot r transpose, which is so r dot r transpose is a little omega. It's the spatial angular velocity. So it's going to be all right. So first of all, so I'll write it out fully and then make the substitution. Okay, so that's just substituting in chi rr. Okay, but this is r dot minus rho, and then this is omega hat times s2. Okay, but omega hat times the vector is the same thing as the cross product of omega with that vector. Okay, like so. All right, so the constraint on the rigid body velocities then is exactly that this thing equals 0. Okay, and so what I've done here is I've expressed This is the velocity constraint. Expressed in terms of rigid body velocities. Okay, so expressed in terms of the translational velocity, r dot, and then the spatial angular velocity omega. Okay, so you know, some elementary manipulations, but you get the thing into a form where the constraint is on the rigid body velocities. Okay, good. And so this thing here, so omega, oops, omega, of course, in this case, given what r is, okay, we've done this so many times before, so we know if r is equal to that, then omega is going to be 0, 0, theta dot. Okay, and of course S2 is 0, 1, 0. And then it's a calculation to show that omega cross S2 is minus theta dot 0, 0. Okay, so you know whatever it is, it has to be in the S1 direction, right? Because the cross product of two vectors always gives a vector orthogonal to the span of them. So in this case, that means it has to be in the S1 direction. So the only question is whether it's plus or minus theta dot. And it's minus. Okay. Right. And so in that case, now what we're going to do is we're going to take that expression and we're going to write it as an expression in terms of constraints on the coordinate velocities. Okay. So r dot is equal to x dot 0, 0, right? Because r is x rho 0, so x dot is that. Okay. And so therefore, the constraints read that x dot is, sorry, I'll write it like this, plus rho theta dot is equal to 0. Okay, so in other words, x dot is equal to minus rho theta dot. Okay, so that's why it's called a velocity constraint, because it's a constraint on the velocities. Okay. And you know, of course, I did this in a super elaborate way, right? So I'll be back to this, sorry. Because of course, you could have just looked at this diagram and immediately written down the relationship between x dot and theta dot, and it would have been, right? So as theta increases, so theta dot is positive, an angle of theta is going to cause you to move in the minus x direction by a quantity of rho integral of theta, right? So you know, you could have guessed that without having to do all this stuff. Okay, good. Now, let's look at another example. And let's look at the disk example, the planar disk example, okay? So that was this thing, all right? Okay, and I did this. Okay, and then I did this, and I forget exactly how I numbered these now. I think it was B1, B2, and B3. Okay, and then I had coordinates. So for this system, I had R as X, Y, rho, where again, rho is the radius of the disk, right? So that's the vector from the spatial origin to the body origin, okay? So that defines the coordinates X and Y, right? They're the position of this point of contact. All right, and then I had a spin angle, okay, which I called theta. And then I had a roll angle about B3, which I called phi. Okay. So you can go through a process which is just exactly like I did here. Okay, there's going to be some changes in detail, and the only real change in detail is oh, there it is, sorry, is going to be this point. Okay, so this point, instead of being x 0, 0, it's going to be x, y, 0. And then this point is going to be 0, 0, minus rho. Okay, so other than that, everything's kind of exactly the same. And what you get, so if you want to see the details of this, it's worked out in the text, but you know, it really literally is exactly the same as this, with the changes you need to make it correct. Okay, so can similarly as above calculate the velocity constraints as, okay. And if you think about it for a second, you can kind of deduce this just from looking at the diagram and squinting your eyes for a second. But what you're going to get is you're going to get the x dot is equal to rho phi dot. And the way I've drawn my angle phi, it's going to be with a minus sign. Okay, cos theta, and y dot is going to be minus rho phi dot sine theta. Okay, so in this case, I get two constraints on the velocity. Okay. All right, so one of the things we're going to explore a little bit is the way in which these two examples, although they're very similar, the way I've treated them, okay, they're very different in one important respect, okay? So in this example, I started out by asking you whether the configuration space was two-dimensional or one-dimensional, and you could easily have said it was one-dimensional. In fact, if you had to model that thing on a homework problem, let's say, you would just make it one-dimensional, right? You wouldn't even think about it, all right? But we're doing it differently. We're making it two-dimensional and then adding in a velocity constraint. But somehow we feel like that velocity constraint really is just reflecting an already existing configuration constraint. Okay. For this one, okay, if I ask you what's the real dimension of the configuration space, right? Because now I have some velocity constraints again. And then the question is so we know that the without velocity constraints, the configuration manifold is four-dimensional, right? X, Y, theta, phi. All right. So the question is, as in the preceding example, do the velocity constraints constrain the configurations? Okay, so in other words, I have two velocity constraints. Is it really the case that Q is two-dimensional, right? 4 minus 2. Okay, the answer is no. Okay, so there's something fundamentally different between these two examples. And that's one of the things we're going to understand. And so questions? When is a velocity constraint really a configuration constraint, as in the first example? Okay, and we're going to give a simple condition that you can use to check that. Okay, and then the other thing is, what are the equations of motion with velocity constraints? Okay, so those are the two things that we're going to spend the rest of the term sorting out.